The current status of our project is split into two teams, the drone and the groundbot team. The drone subsystem has completed drone kit navigation, XP radio communication, and database management through Python and the Raspberry Pi. The groundbot subsystem has navigation, plant vital measuring, basic XP communication, and have added a GPS to be used for navigation. Incomplete goals for the drone: we have to complete navigation through the use of image processing to determine GPS coordinates. We will be using the PixieCam, and we'll be determining the location of resources to be used for navigation. For the ground bots, we have to complete navigation to GPS waypoints and fully integrate the XP radio communication to talk to the drone. Afterwards, we would do some full system testing to make sure all the components are working.
There are many territories that are difficult or impossible for human habitation. Areas such as desert and outer space have really harsh conditions that limit human exploration. Therefore, robots are the perfect substitutes to explore those places. Our plan is to create a vehicle system to carry plants and ensure their survival in harsh conditions. It paves the path for future human civilization to expand their inhabitants.
Our project incorporates an unmanned ground vehicle which safely transports a plant to a resource-rich location within an unknown environment which has been designated by a drone. The ground vehicle takes regular vital sign checks of the plant to ensure that it is in good health. In the event that it requires a resource such as water or sunlight, it sends a signal to the drone, which then goes out in search of that resource. Once the resource has been located by the drone, it then communicates the location of it back to the ground vehicle, which activates its own navigation protocols to safely transport the plant to the resource location.
So how does the system actually work? There are three main subsystems: the drone, the ground robot, and the communication system that links them together. We outfitted an off-the-shelf quadcopter with a Raspberry Pi and the Navio 2 flight controller, along with the Pixie 2 camera to act as our vision sensor. These components allow us to program the drone with Python scripts without the need for a ground station. Everything is self-contained on the drone. We designed and 3D printed all the mounts since off-the-shelf components didn't exist for these. The ground robots are custom made from aluminum for the chassis and off-the-shelf motors and wheels for movement. They are controlled with Arduinos running our own obstacle avoidance and navigation algorithms that make use of ultrasonic distance sensors and the BN880 GPS compass combination module. Now, the communication system must be robust in that no information is lost or corrupted in order to ensure that the groundbot doesn't go totally off course. It also needs to be fast with less than 1 second response times, so the drone and each ground robot in the fleet are outfitted with an XB S20 radio that actually takes care of data integrity by itself. All we need to do is give the radios a payload and the destination. In our case, the payload is a serialized JSON object that follows our own lightweight protocol that allows the groundbot and drone to classify the types of resources that they need or the resources that they find. Integrating these three major subsystems together, we have an autonomous, expandable system for unknown territory exploration.
On the left, we see the drone's current functionality. For additional functionality, we would first improve the resource tracking algorithm. We are changing this algorithm to control the drone's movements using velocity instead of position control. This new algorithm is currently in the debugging stage and is constantly accounting for error, which would give us a more accurate GPS location. Along these lines, we would also like to stream video from the Pixie camera so we could see what the drone sees. This would help us determine if the drone is behaving as we expect, especially under complex conditions such as multiple resources detected in the same frame. We would also like to enable the drone to pick up and drop off payloads in the event that a ground vehicle dies. However, this function is not going to be completed this semester due to time and money constraints. The improved resource tracking will be completed and the video streaming will be attempted. This work can be done at an individual's house, but testing needs to be done in an open field when the quarantine restrictions are lifted.
So right now for the ground team, we're actually really close to finishing GPS navigation for 2 of our ground bots. We only need to purchase a few more gyroscopes and then we can start implementing XP communication for our project. Unfortunately, there won't be any space at home to actually fly a drone, so what we'll do is we'll use the drone complete with both XP and GPS as a waypoint for our ground bots. And our final presentation might look something like this. We'll have 2 of our ground bots head towards the resource, which is represented by the drone's GPS coordinate, while avoiding obstacles along the way and checking on plant vitals as well. And if we're allowed more time, we might look into resource identification using PixieCam or OpenCV and have the ground bots actually move towards a resource instead of a GPS point.